Okay, so just to summarize, what we were trying to achieve is we were trying to achieve a system where, you know, where your flaps at a 90-degree angle, we're okay with that, that's allowed. Where we are pushing on them and allowing that liquid to go down into ventricle, that's fine. But what we didn't want to happen is for those flaps to open, sort of, you know, go beyond 90-degree angle and allow that liquid to go back upwards. So I don't want that to be happening, right? And usually people come up with a few solutions, so we discussed a number of these solutions. So Terry, you had this idea of one flap being longer than the other and kind of them sort of jamming each other. But, you know, I was trying to kind of visualize it, and as I said, you know, it doesn't necessarily, it might be an issue in some, it might be a solution rather to this issue in some systems. But when I'm thinking about the heart, because of the pressure, you potentially could just have that kind of thing happening. So even if they overlap, they're not going to necessarily stop, you know, at that 90-degree angle. Another solution which a lot of people usually think of is they're visualizing doors in their house, and they think, right, if I have frame, and frame is stopping that door swinging, you know, at 180 degree, I want it just to stop at 90 degree. You might have like a little bit of wood or something just like a wedge of which would stop those swinging any further, which is again could have been a solution. The only issue is that the flaps of tissue in your heart, they're not rigid like your doors, so you could still have them kind of swinging that way, right? Even if you did have something solid there to try to stop it. So the solution which Nate came up with, right, is a slightly different one. And well done to anybody who thought of it, or if you're watching my video. So another potential solution would be to attach a bit of string. How about that? If I attach a bit of string there and there, can you see how that can resolve this issue? And just to illustrate it, let me just grab another little model. Made of the same high-tech material, right? So let's compare the two. So that's where we started from, right? Where I'm allowing liquid to go through, but the issue is I also was allowing it to go up, back into the top chamber. Whereas this one, where I've got two bits of string attached to the flaps, right? What that does is I'm allowing still liquid to go through, but when I'm trying to push on them, those bits of string, because they're a certain length, they're stopping those flaps. Can you all see that? And from experience, quite a few people think of that solution.
It's like those fold-up things in some trucks.
Right.
Like
So it's a bit like, Terry, what you were suggesting, with that you know, metal bit which is attached to some doors, which again stops it from swinging. So in that sense, you were very, very close to that solution, right? So this is what you have in your heart, which solves that particular issue. So, does anybody know what these bits of string are called? What do we call it? Any bright ideas? What are they called? These strings. Anyone? No?
I feel like if you tell me...
Oh, you know, I already gave you half a name for them. Oh, no, it's nothing complicated. So we have a name for them in everyday language. Promise. Right? She's saying she's playing on my heartstrings. Right? So they are... Right. So they're known as heartstrings. Okay? So heartstrings are not just figure of speech, they're actual physical you know, structures within your heart which are stopping those cusps from you know, opening into the atria. There is obviously a technical term for them as well. So the proper technical term comes from Latin, and the term is, I'm going to try to spell it correctly, it's cor diatendinum. So it's a bit like a cord and a tendon. Yeah, so it's sort of just these are the origins of these words. So why tendon? Because they're made out of really, really strong connective tissue, which is similar to, in appearance, to tendons. And if we're lucky enough to have a look at the actual heart, which I'm hoping I'll be able to get a heart, and just at least show you if we can't have proper dissections this year. But you will be able to see those heartstrings. Okay, they're really well visible and they're incredibly strong. I mean, they look very, very thin, but in terms of, you know, if you try to break them with your hands, they're almost impossible to break. Yeah, you have to have scalpel and really kind of go for it and hack at them to be able to cut through them.
You can like put your, like, well, you can tend to like put your finger under them and like the weight of the heart, like hanging with gravity.
Yeah,
it does
yeah,
like nothing
yeah,
to it.
absolutely. They are incredibly strong. And they need to be strong in order to withstand that pressure, because when the ventricle is contracting, it's really pushing on those cusps, and they need to stay at this 90-degree angle and not give in. Because if they do give in, then you have a heart issue, then you have a heart condition. Because you're allowing that blood to backflow into atria, which is no good idea.
So the heartstrings stop the cusps from backflow?
If you didn't have those heartstrings, you would be allowing black flow of blood, right? Because you would have that kind of situation, you see? Where I'm allowing some of that blood to go back up into atria, and I don't want that to happen. Okay? Right, so I'm going to now wipe this side, because I'm going to use it to talk about the second type of valve. So this is all information about still atrioventricular valves, right? The ones which are found between atria and ventricles. So now, let's start talking about the other type. So the other type are called semi-lunar valves. Semi-lunar valves. Again, often abbreviated to SL, so capital S, capital L. And again, you've got two of the semi-lunar type. So two of this type. So altogether, in total, I have 4 valves. 2 AV, 2 SL. So 4 in total. Now, where do I find these valves? These 2 valves are found between ventricle. So let's talk about one side at a time, maybe. So on your left side, the semilunar valve is found between left ventricle and aorta. So it's basically into at the entrance into aorta. And because it's at the entrance of aorta, it's also known as aortic SL valve. So the specific name is aortic SL or semilunar valve. And then on your right side, it's going to be at the entrance into, what do you think I'm going to be writing next? So if I'm leaving right ventricle, where am I going into? Which blood vessel? Have a look at that diagram we did earlier in the lesson. So from right ventricle, where is that blood going to go? Have a look at the diagram we had earlier in the lesson, yeah, where we had all the blood vessels labeled. So right ventricle, what's the name of a blood vessel there?
The pulmonary artery.
okay? Or before it splits into right and left pulmonary
Pulmonary
arteries,
trunk.
pulmonary trunk. So right side, you're going to be at the entrance into pulmonary trunk. So, and again, because of that fact, the specific name for this SL valve is going to be pulmonary SL valve. Okay, so SL valves, they're designed a little bit different to AV valves. They're still stopping backflow of blood, but they work on a different principle. And this is, again, this is where you need to kind of try to visualize things. Now imagine this circle is where I'm looking from left ventricle into aorta. So that's the opening, and I'm trying to get into aorta. And that's where you find aortic SL valve. So the kind of shape it's going to have is going to contain 3 flaps of tissue, and when a SL valve is closed, those 3 flaps of tissue are going to, did I say closed? Didn't I, right? So when it's closed, these 3 flaps of tissue are going to be like little sort of slivers of tissue lying flat against the walls of aorta. Okay? So this is opening into aorta. So these are going to be my 3 cusps. So cusp. Right, and I wonder also, let's sort of try to break down the name a little bit. Semi, what does that mean? If you have semi-detached house. Half, right? Half. What about this bit? Lunar.
Full?
Hmm?
Full?
Mm-mm.
Like a hole? It's like the moon.
Moon, exactly, so this is moon. So in essence, semi-lunar simply means half moon. So when your valve is open, so that bit in the middle is the opening where the blood is allowed to flow through. But what happens when it's closed is those 3 flaps of tissue, we're going to extend towards the middle point. So each cusp is going to do that kind of thing. So they're going to extend towards the middle. And so each one looks a little bit like half moon. So this is a bit like a crescent of a moon. This one is half moon, hence the name semilunar. So this is when the valve is closed. Okay. If you have a color, you could actually color it in as well, just to show them more clearly. So all of that is going to be on 3 cusps. Can you visualize it? Right, so imagine my opening, the 3 cusps, and then each one is going to kind of extend towards that middle point. Overlap, yeah, exactly, slightly overlap. So it works a little bit like shutters on these old-fashioned cameras. I do not know, maybe I'm a bit too old and I can still remember them. When you used to press a button to take a picture, you could see there were like a little plastic, I don't know, plates, I suppose, which would extend towards the middle point. That would give you the shutter in these old cameras. So it works a little bit like that. Now, can you see on this diagram there is a little bit of a problem? What's the problem?
There's a small gap.
Can you see there's a tiny little triangular gap? Can we allow that? No, not really a good idea. So nature came up with a solution. As usual, right? Nature is a really good engineer, so any engineering problem is going to come through evolution and overcome this issue, the same as we had those heartstrings overcoming the issue of flaps moving too far. So what you have is kind of 3 bits of connective tissue. sort of in that sort of position. So you can visualize when three cusps are going to come towards that midpoint, those three bits of connective tissue, so-called nodes, so node of connective tissue. So these three nodes are going to pretty much close that little awkward triangle. And so the backflow is fully eliminated. Okay, so this is the information about sort of design, the structure, and the function of the valves. So AV valves and SL valves. Okay, so I've got a next little challenge for you. Can I wipe this information off now? You've finished with copying it. Okay. So let me just do that. So my next little kind of subsection is going to be called cardiac cycle. Cardiac cycle. Cardiac cycle. I'm going to give you a slightly simplified version of the cardiac cycle. And if you wanted to research further, please do. Okay? So we are going to just concentrate on what ventricles are doing. If you want to talk about what atria are doing, you can do in your own independent research, but it's not the key. Why is that? Because ventricles are the chambers which are doing by far the most work. And so a lot of information in books applies to description of what ventricles are doing and how they're involved in cardiac cycle. So when it comes to ventricles, they're either contracting or they're relaxing. Okay, so contraction of ventricles and then relaxation. So contraction of ventricles and then relaxation of ventricles. Does anybody know what kind of terms are given to contraction and relaxation of ventricles? Does anybody know? You probably heard these words before, particularly if you're already working within a healthcare setting. Anybody's got any guesses? Because depending on whether you're contracting ventricles or relaxing ventricles is going to give you two different readings for blood pressure. I'm really giving you some clues here. Right, systolic and what's the other one called? Yeah, go on.
Dystolic.
Dystolic, right? So the name for contraction, do you know which one is which, by the way? Which one is higher, systolic or diastolic pressure? Any idea?
The one on the top.
Yeah, so which one is that? Is that systolic, the top reading?
Yeah.
Yeah, absolutely right. So therefore, yeah, absolutely right. So if you think about when you're measuring your blood pressure using one of those blood pressure machines, right? So the top reading is your systolic pressure, bottom reading is your diastolic pressure. So let's try to figure out, therefore, so what's going to be contraction of ventricles? Is that systole or diastole? So when I'm contracting, what am I expecting for pressure to do? High, right? So this is your systole. And therefore, relaxation of ventricles is going to be a diastole.
I recognise that now.
Yeah, do you recognise these words
My
now?
teacher said it differently, and that's why at first I
Okay.
didn't.
Well, you can say systole, diastole. I don't know. It depends on how you're used to pronouncing it. It's just the way I'm used to pronouncing it. What did I want to say? Sorry, I lost my track of my thoughts now. So these two terms come from Greek, by the way, and just they literally mean contraction, relaxation in Greek language, and hence the diastolic pressure and systolic pressure. Okay? So here is my little challenge for you. Okay, so can we draw a quick table? Don't we draw, unless you're really sort of obsessed by a thing being super neat. So really simple table. So we're going to have systole here, diastole here, and then I'm going to write AV and SL. What do you think AV and SL mean?
Vowels.
Right, the valves, so AV, atrioventricular valves, SL, semilunar valves. And what I'd like you to do, and please do not go for books or websites or anything like that, just use purely your notes and a bit of common sense, and it just requires a little bit of visualization and thinking about things in a logical way. In each of these 4 squares, I want you to either put the word open or put the word closed, that's all. Make sense? Okay? So I'm going to leave you to kind of think about, so when I'm contracting ventricles, what do I want AV valves to be doing? What do I want SL valves to be doing? And the same for diastole. Okay, so that's a bit of a challenge one for you to complete next.